So in yesterday's class, what are the things we have covered are first of all, we have covered the stress tensor, the stress that acts at any point inside a body at any arbitrary angle of any magnitude can be divided into 9 stress components, assuming the body to be a simple parallelepiped, and on the faces the stress components are acting. There are 3 normal stress components, there are 6 shear stress components, and total 9 components that make the stress tensor. When we write a stress tensor component as sigma ij, that is sigma xx, sigma yy, sigma xy, sigma zx, whatever, the first term I represent the plane on which it is acting. And plane means we say that the plane that is perpendicular to the x direction, we call it as x plane. XYZ can also be written as 1, 2, 3. So plane perpendicular to the y direction is y plane. And the second term J represents the direction along which the stress is acting. So I represents the plane on which it is acting, and J represents the direction towards which the stress is acting. Now, for the body to be under static equilibrium of forces, because I said that there can be 2 different situations, a body can be under dynamic equilibrium like a moving car. So in dynamic equilibrium, stress doesn't develop, so deformation possibility is not there. But if it is under static equilibrium, it is stationary and you are applying stress, then there needs to be force balance and moment balance. Forced balance gives certain equations that we have derived. Moment balance tells that sigma ij equal to sigma ji. So the stress tensor is symmetrical. Therefore, if you know the 3 normal components and any 3 shear components, you can write down the entire stress tensor. So there are 6 independent stress tensor components. Then in the next discussion, we have covered that we try to derive the resultant stress acting on any arbitrary inclined plane, because plane number 1, 2, 3 or xyz are basically my face planes of the parallelepiped, 3-dimensional body. So any arbitrary plane that is inclined with respect to 3 major axes with direction cosines of alpha 1, alpha 2 and alpha 3, that means the angle between plane normal, that particular plane normal, and the direction 1, if it is theta 1, then alpha 1 equals to cos theta 1. Similarly with direction 2, it's theta 2, and direction 3 theta 3. So alpha 2 and alpha 3 are cos theta 2 and cos theta 3 respectively. We considered the plane ABC, and we have showed that the resultant stress that will be acting on the ABC plane will basically depend on the stresses acting on the 3 faces of the body, because primarily the stress is acting, net stress is acting at the point O. So here we are showing the stresses acting on different faces and how to express the net stress on the ABC inclined plane, and net stress sigma that can be divided into either sigma n and sigma t components on the ABC plane, normal and shear component. It can also be resolved into sigma 1, sigma 2, sigma 3, 3 components along 3 major directions. So sigma square equals to sigma n square plus sigma t square. 1 minute, please. 1 minute. Hello. Good morning. বলুন। আমি পৌঁছে গেছি। কাজ করছে, কাজ চলছে তো। কাজ চলছে। ঠিক ঠিক তাড়াহুড়ো না করে করুন, আপনি চিন্তা নেই, আপনার পেমেন্ট সুন্দরভাবে আপনি পেয়ে যাবেন। একদমই চিন্তা করেন না। ওইটাই বুঝতে পারছি। আমি বুঝতে পারছি, কিন্তু কিন্তু ওই জন্য আমি আমি বুঝতে পারছি, কিন্তু আপনি কোনো চিন্তা করবেন না। যদি নাও হয় 2-3 দিনের মধ্যে আপনি পেমেন্ট পেয়ে যাবেন, ঠিক আছে? আর যখন মেশিন পৌঁছে গেছে, আর আসলে বুঝতে পারছেন তো, অফিসিয়াল একটা ফর্মালিটি আছে, একদম কিছু না, মেশিন দাঁড় না করিয়ে একটা ছবি তুলে আমি পাঠাতে পারি না। একটা ছবি তুলে, ওটা নিয়ে আর চিন্তা করবেন দাদা, আমি ক্লাস নিচ্ছি। সেটা তো ঠিক আছে, ঠিক আছে, আপনি কোনো চিন্তা করবেন না। ও সব সব বুঝতে পেরেছি, হয়তো 30 তারিখ হবে না, কিন্তু খুব তাড়াতাড়ির মধ্যেই হবে। প্রসেস একটু আছে, খুব তাড়াতাড়ির মধ্যেই হবে। আমরা কখনো ভাবেই আপনাকে অসুবিধা করবো না। নিশ্চয়ই। ঠিক আছে। ওকে। Yes. So we have now, so sigma square equals to sigma n square plus sigma t square equals to sigma 1 square plus sigma 2 square plus sigma 3 square, because whether you take the direction n and t, they are mutually perpendicular. 1, 2, 3 are mutually perpendicular. So we have tried to express the stress acting on that plane through components, and we have written this expression only considering direction 1. So this expression we have considering force balance along direction 1. So all the stresses we have considered along with their area of those planes on which they are acting. So that we equated with sigma 1 delta, because the ABC plane has an area delta. The other 3 planes that we considered had area delta alpha 1, delta alpha 2, delta alpha 3. Now that sigma 1 basically comes from sigma n and sigma t, they are components. Here we have discussed about the importance of principal plane, because we now want to derive what is the principal plane. So principal plane is the plane on which there is no shear stress. So the stress is only normal stress, and the normal stress value can be 0 also. It can be positive, it can be negative, but that is the principal stress. So if the plane is principal plane where there is no shear stress, then the shear term cancels out. We crossed the shear terms and made that 0. So now entire stress that is acting as normal stress. So we can write sigma n equal to sigma. So basically the stress that is acting on that plane is perpendicular to the plane along the plane normal. So sigma n we are replacing by the term sigma, and we have obtained an expression, and for 3 major directions, 1, 2, 3, 3 such expressions can be obtained, which are written here. And if we take sigma on the other side, it becomes sigma 1, 1 minus sigma alpha 1. So the 3 equations become this, and the 3 equations can be to solve the 3 equation, their determinant can be equal to 0. So now if I expand that determinant, it comes into sigma cube plus a sigma square plus b sigma plus c equal to 0 form, where a, b, c are absolute numerical values, because sigma 1, 1, sigma 2, 2, sigma 3, 3, these stresses are actually the absolute values. The stress values acting in different direction, having an unit same PA or KSI or whatever you take. And ABC are called invariant because they are independent of the coordinate system, how you choose the coordinate. So this expression has three solution: Roman 1, Roman 2, Roman 3, and conventionally Roman 1 is taken as maximum one and Roman 3 is the minimum one. Two of them can be equal also, even three of them can be equal also. So after that, we have considered more simple case where plane stress, where there is no stress is acting along the third direction. So there the determinant becomes sigma 1 1 minus sigma 2 1 1 2 to 2 minus sigma equal to 0. This is a square form, so sigma square plus a sigma plus b form it can be written, and using the Sridharacharya's formula you can get the two solution where the maximum value plus sign is taken as sigma Roman 1, maximum principal stress, and another value is sigma Roman 2, the second principal stress. Third do not exist here because it's a plane stress condition. Then we talked about the maximum shear stress. Maximum shear stress acts at a 45-degree with respect to the principal stresses, principal directions, and maximum shear stress is basically the difference between the principal stress. That is tau max equal to sigma 1 minus sigma 2 by 2. So if the three principal stresses are same, that is hydrostatic, cylindrical, and three are different, that is triaxial. So we have talked about the importance of maximum shear stress, as majority of the slip occurs along 45-degree with respect to your principal loading direction. We then discussed about the Tresca's criteria, as Tresca has mentioned that yielding occurs when maximum shear stress equals and exceeds a critical value. So that is the general formulation. So we can write that tau max equal to sigma 1 minus sigma 3 by 2, because out of the three maximum possible, this is the maximum value that we get, because sigma 1 is the maximum, sigma 3 is the minimum. So that exceeds any particular value k. And this is a generalized expression, so it is applicable to any loading condition, tension, torsion, bending, shear, whatever. So now if you consider the simple tension, yielding occurs when sigma 1 exceeds sigma naught, where sigma 2, sigma 3 equal to 0. So k value comes out to be sigma naught by 2. So the expression of Tresca talks about sigma 1 minus sigma 3 to exceed sigma naught. And if we consider the value of the torsion case, where sigma 1 equals to minus sigma 3, and both of them has to exceed tau naught, which is the shearing yield strength. Sigma naught is the tensile yield strength, uniaxial tensile yield strength under uniaxial tensor. So relation comes tensile yield strength equal to 2 times the shearing yield strength following Tresca yield criteria. We have talked about principal stress tensor can be divided into two different parts. The all equal part is called hydrostatic stress tensor. Hydrostatic stress does not cause any plastic deformation. It only leads to elastic deformation and volume change. If it is a net compression, then it is a volume will decrease slightly. If it is an expansion, volume will increase slightly, like what happens in vacuum or in under sea. In air also, we are under some kind of hydrostatic compression. So the remaining part becomes stress deviator component. If I subtract the hydrostatic stress tensor from principal stress tensor, we get stress deviator tensor, which is actually responsible for plastic deformation, and therefore von Mises considered that. So von Mises tried to determine the invariance for this stress deviator tensor, and he said the second invariant. So if we consider that again, we try to determine the principal components from that stress deviator tensor, then again that kind of expression comes, that sigma minus sigma 1 minus sigma h, something like that, equal to 0. You expand whatever you get, that is of not much importance. But von Mises said second invariant, that is J2. So yielding will occur when J2 equals and exceeds a critical value. Therefore, the J2 form is written either in terms of stress tensor form or principal form. In both way you can write it. And second invariant reaches a critical value, and it is also applicable for a general case and one of the cases like uniaxial tension. If you consider tensile condition, you take k square, k, whatever constant you take, ultimately you will come down to this form of an expression. 1 by root 2 under root sigma 1 minus sigma 2 square plus 2 minus 3 square plus 3 minus 1 square greater than equal to sigma naught. So the beauty of this expression is whatever principal stress you apply, if your stress is equal in all direction, whatever be the magnitude, 1 MPa, 1 GPa, 100 GPa, 1 million GPa, if sigma 1 equal to sigma 2 equal to sigma 3, there will not be any plastic deformation, because your sigma naught will not be considered until and unless there is a difference between the principal stresses. So for distortion or deformation to happen, there should be a stress imbalance. The stress in all directions should not be the same. There should be a difference between them. And more the difference, easy, at a lower stress, applied stress, you will get the deformation to occur. So we have concluded that for different loading condition, there can be yield stress, and the yield stress value will be different. So von Mises criteria, if you follow, the shear, yield stress under pure shear will be 1 by root 3 times of the yield stress under uniaxial tension. But Tresca said it is half. So there is a little difference, and we said that basically these are predictive equations for solid mechanics point of view, solid continuum mechanics. These do not consider atomistic theory or microstructure and other effects. So these are basically predictions that we use for design. And von Mises prediction is more accurate because it's considered three principal components: sigma 1, sigma Roman 2, Roman 3. But Tresca is more simple because it considers two components. So these are their strength and weakness. So this understanding is necessary. Now today's lecture, I will try to discuss a bit about the strain. So yesterday we have covered stress. Today we will cover strain. To start with, we will not use the word strain. We will use the word displacement. So what we are showing here in this plot is a point which was at P. Basically, the point P is moving to a new position, and the new position is P dashed. So P point has a coordinate x, y, z in Cartesian coordinate, and it has moved to a new position P dashed with a new coordinate x dashed, y, z, and z dashed, where x dashed equals to x plus u, y dashed equal to y plus v, z dashed equal to z plus w. So UVW, basically UVW represent displacement along the three major direction. So along x direction, point P has displaced by an amount of u. Along y direction, point P has displaced by an amount v, and z direction, it has displaced by an amount w, so that the point P reached to P dashed position. So to start with, we will not use the strain term, because you will realize afterwards where I am not using the word strain. Rather, to start with, I will use the word displacement, and more specifically relative displacement. That means with respect to the initial position or initial length or something, how much is the change in terms of displacement? Because if you consider deformation or simple translation, whatever, basically one point is moving into other point, and there will be a permanent change. One point is more, or even in elastic deformation, that is true. One point moving into other point. So now let us see, initially the body was having, suppose, a length L naught. You may consider this one has a length L naught. And within the initial, say this is your initial gauge length, one end is hinged, one end is fixed, you are loading from the other end. We are considering 2 points, A and B. 2 points, A and B. So now under load, if it is get stretched, what will happen? You see, A point will shift to A dashed from here to here, whereas B point, which was somewhere here, it is now shifted to B dashed. So the interesting thing you will find is the point that is farthest from the hinged portion will shift more, because basically a point which is here very near to the hinged end will shift minimum. That point will or the point that is touching the wall, that point is basically not shifting. But the point at the other end, as you go along this direction, x direction, you will find the points are shifting more and more. For example, if you take a point here, that point will now shift to here. So this much is the shift of that point, whereas a point that is tightly attached with the hinged point, that is not shifting. So we will find the points are shifting. Initially the length was AB. Now the distance between these 2 points become A dashed B dashed. So relative displacement can be written as A dashed B dashed minus AB divided by AB, because the new distance is A dashed B dashed. Initially they were separated by AB, so total net displacement is A dashed B dashed minus AB, that you have to divide by the initial distance AB, and that you will get relative. So note the word relative, it is not the displacement that we are mentioning. Displacement is A dash B dash minus AB, but relative displacement you have to divide with the original distance. And one more important thing is, more you move towards x direction, more you move from here to here in this direction, along the longitudinal direction to here and here, you will find points are moving more and more. So there is a direction of movement, and there is also something called proportionality of the displacement point. That means in this case, the point is moving along the direction x, and it is also proportional towards the direction s. More you go towards the direction x, you will find the point is moving more and more. So for example, you take here in this diagram where a 2D, we are just taking xy plane, and on the xy plane we are showing a body. Initial the body is indicated by red color dotted lines, and final position of the body is indicated by blue color line. So initially the body was something like this, as mentioned by the red color dotted, and if you stretch along the direction x, it will now squeeze along y direction, and it will extend along the x direction. So initially 2 points, if I can take 0 and P, O and P, and after it is stretched, O point remains at the same position, whereas P point moves farthest to P dashed position. And any point in between O and P will go through displacement which is more than the O point but less than the P point. So the displacement is happening along the direction x, and it is proportional to the direction x. That's why whatever the relative displacement that we get from this, we express it in this form. We write it Exx. This is relative displacement that is shown in this plot. We write it as Exx, where the first x, so if I write it in a more general form, Eij, there the I will actually stand for the direction towards which the point is moving. So here the point is moving towards the direction x, and J stands for towards which direction the movement is proportional to. Here the movement is also proportional to x direction, because when x equal to 0, displacement is 0. when x equal to x, displacement is p dashed minus p. So the displacement is increasing with the increase in x. That's why we write it as sigma xx. And how to represent that? Suppose inside that body I consider a small length dx, any arbitrary length inside the body. Suppose my initial uh, body, that length is dx. Now inside that I consider a small volume element. I consider a small element, that is delta x. A small distance inside that dx length is delta x. And suppose I am stretching, and as a result this delta x length is getting extended by a small amount delta u. So the displacement that is happening with respect to the small length delta x is delta u. So what is the relative displacement? So to know the relative displacement, we first need to calculate what is the total displacement. So if a del u is the small displacement with on a length del x, then on the length dx, how much will be the total displacement? Del u by del x into dx. So this is the total displacement on the entire length dx. So we write total displacement and divide it by dx, because dx is also the initial length. So displacement divided by initial length is my relative displacement. So how much is the relative displacement in this case? Sigma xx. Sigma xx is equal to del u del x. So del u del x will give my relative displacement along the direction x, which is proportional to the direction x. So exx is del u del x, where u is the displacement along the x direction. Come to another situation. My initial two-dimensional body is represented by red color dotted lines, and I am applying a shear stress. You see, here I am applying a shear stress. I am applying a shear stress. And when I am applying a shear stress, the body is getting sheared, and the new position is represented by the blue color line. So we see there is a strain, and this strain is represented here, and it is written here. So how to represent that strain? Please note that strain is written as EXY. So, or I will not use the strain, sorry, I will use the word relative displacement. I will use the word relative displacement. Till now I am not using the word strain. Apology. I should not use the word strain. It's relative displacement. So EXY, why I am writing EXY? Because the points are shifting towards the direction x, and therefore the first term is x, and this shift is proportional to the y direction. If you see the displacement at this point, how much is the displacement along x direction? 0. More you increase the y, if you move along the y, you will find the points are shifting more and more. That means the displacement is happening along the direction x, but it is proportional to the direction y, and that's why the second term is y. The displacement is proportional to which direction? That is y. And we will write this in the form of del u del y, because displacement along x, we know that we write it as u, and since it is proportional to y, so this component I will write it as del u del y. Similarly, number 3 direction, as I arrowed here, we are applying a stress along y direction. The initial body red dotted, it changed to the blue. So we are finding that there is a net relative displacement. That is, relative displacement is EYY. It's happening along the direction Y, and it is proportional to the Y as well. So that term is del V del Y, del V del Y. But one thing you please note, that the displacement is not only that. When this is happening, there is also a displacement along this direction, which is EXX. EXX in negative direction, if the constancy needs to be maintained. So as a body is stretched, its cross section or its thickness or width also has to come down. So if you apply a stress, say I am writing this stress at sigma YY. So sigma YY stress not only cause a strain EYY along the direction Y, but it also leads to a displacement, relative displacement EXX. Similarly, in this case, the stress that I am using is sigma XX. So if I apply a stress sigma XX, it's not only causing relative displacement along x direction, which is EXX, but also relative displacement along y direction, that is EYY, in a negative sign. So longitudinal displacement and transverse displacement. Come to the final picture. Here I have applied a shear in this way, and it has led to a displacement which we write as EYX, because the displacement is happening along the direction Y, but it is proportional to the direction X. Shubham, am I audible? Hello?
अच्छा, और सर का आवाज नहीं आ रहा क्या?
Shubham, am I audible?
Connection problem.
But you are audible to me.
I am audible.
Yes, sir, you are audible, sir.
हाँ, वही मुझे डर लग रहा.
Shubham, is the recording going on? Hello?
Sir, I think has a problem, net problem. Recording is going on.
Okay. And I am audible. Can you hear me?
Yes, sir.
And can you see the canvas screen?
Yes, sir. Yes, sir.
Okay. So I am continuing.
Okay.
So this displacement is EYX equal to, because displacement happening along the direction Y, and we know that displacement along Y is represented by V. So we will write it as del V del X, because it is along the direction Y. So the displacement magnitude is V del V over a small distance del X, because it is proportional to X. So now all the displacement terms, relative displacement terms, I am writing in the form of a tensor. So we call this tensor as relative displacement tensor. EIJ is relative displacement tensor. This is my relative displacement tensor. Relative displacement tensor, and the terms are written as E11, E12, E13, 21, 22, 23, 31, 32, 33. You can also write them in the same way as XYZ. EXX, EYY, EZZ, EXY, YX, like that. And all the terms are represented in terms of displacement derivatives. That means EYY equal to del U del X. E12 is del U del Y. E13 is del U del Z. E21, whenever you think 2 means V is the displacement along Y. So del V and then 1 proportional to X. So del V del X. E23, that means del V, del Y, so on and so forth. E31 is del W, del X. E32 is del W, del Y. E33 is del W, del Z. So this is my relative displacement tensor. Now in the next canvas screen, you will understand why so far I am a bit hesitant to use the word strain, and whatever I am saying is relative displacement tensor, relative displacement tensor. Because how will you represent this condition, what I am arrowing? How will you represent it? Do you think in this case the initial body was in dotted red line, and after displacement the body is represented by the blue line? So do you think that there has been a strain in that body? Has the body deformed? No, the body has not deformed. The body has not deformed. You have applied, you have done something, and it's get rotated. So basically this condition is no deformation but rotation, simple rotation. And whenever there is simple rotation, you are getting those displacement terms because the points have displaced. So you are finding here there is a displacement along this side, which is represented by E xy along the direction x proportional to the y, or you can write it as E12. Similarly, there is a displacement along this way, and that displacement is basically Eyx or E21, because the displacement is happening in the y direction, negative y direction, and it is proportional to the x direction. But do you think the body has deformed or strained? No, no strain. You have just rotated it. So displacement can come from three different aspects. One is where from displacement can come. Displacement can come from three different aspects. What is one? One is, we write it as translation. If you take a body from one position and put it in some other position, you take a chalk from one location and put it in some other location, that is called translation. And you will find that kind of displacement because the point x is moving into x dashed or p is moving into p dashed. But that aspect can be taken care of very simply by moving the coordinate along with that body. So if you fix the coordinate along with that body, then you can take care of that, because with respect to this coordinate, there will not be any displacement or any change. So translation can be taken care of by simply attaching the coordinate with the body and moving the coordinate along with the movement of a body. Then what else causes displacement of a point? As we said, rotation can cause displacement. Rotation, I am writing ROT. Rotation can cause displacement. Here, what happened is basically the rotation. And carefully see, when there is a rotation, what happened? There is a positive EXY and there is a negative EYX. EYX move in this side, which is the negative side. So total angular change on the XY plane can be represented by EXY minus EYX. So whenever there will be a rotation, there will be a minus sign between two components of relative displacement tensor. So if you consider the total angular change on a particular plane, xy or xz or zy, you will find rotation. When there is a rotation, then there will be a total angular change on the plane will be one positive component minus another negative component. Exy equal to Exy minus Eyx is your total angular change on that plane. On the other hand, in the second situation, which is represented by the tick that I made, here also I am showing the xy plane. I am showing the initial body as a red dotted line. And you can see when I have applied shear in both sides, I've applied shear this side, I've applied shear this side. This is the real deformation. So here the deformation has happened. So displacement can also happen because of deformation or strain. So far I was using the word relative displacement, which comprises of three possibilities: translation, rotation, and deformation. So this is an example of deformation. And in deformation, you will find you are getting one component that is Exy, you are getting another component in Eyx, and both are positive. So total angular change, which is represented by the gamma term, gamma is called, basically gamma is used to represent shear strain. So total angular change on xy plane because of shear is the sum of the two relative displacement components, Exy plus Eyx. Whereas when it was rotation, then the total angular change was minus. So now I can divide the displacement tensor, relative displacement tensor, into strain tensor, that is deformation tensor, which I am writing as epsilon ij, and rotational tensor Rij. What I have to do? Simply with each term, say each term ij, Eij, I can write it in this form: Eij plus Egi divided by 2 and Eij minus Egi divided by 2. Simply by this way, I can write the term. I can write one part as plus minus. So if you add these two, you will find you are getting Eij. So basically the relative displacement tensor I am dividing into two tensors, one tensor containing plus term and one tensor containing minus term. So see, the tensor that containing plus term, epsilon ij, now I am using it strain tensor. So this particular tensor is my strain tensor. You can call it as strain tensor because here the angular changes are represented by plus terms only. Strain tensor. First term will be del u del x. Okay. Because Exx plus Exx by 2 plus Exx minus Exx by 2, which is Exx, which is del u del x. Second term, what is that? I'm taking only the plus sign terms. Second term has to be Exy. So Exy plus Eyx by 2. Whereas the rotational tensor, what is the second term? Rotational tensor, second term is Exy minus Eyx by 2. So you will find in strain tensor, the term is del u del y plus del v by del x divided by 2. Okay, come down to the first term of the second row. First term of the second row as I have hatched. What is the term? That term is basically Eyx or Eyx. So what is Eyx? Eyx means del v del x. So now in terms of sigma epsilon ij strain tensor, this term becomes del v by del x plus del u by del y by 2. That means this particular term and the second term of the first row, they are basically the same. Similarly, you will find this particular term, third term of the first row and the first term of the third row, representing angular changes due to shear. These two are the same. Similarly, you will find the third term of the second row and second term of the third row are basically the same. And it is very nice to represent the tensor in this form, because the strain tensor is now showing up as a which kind of tensor? Symmetrical tensor. It is showing up as a symmetrical tensor. And you know, stress tensor is also a symmetrical tensor. And you also know that stress causes a strain, or from strain you can calculate stress. So if stress tensor is symmetrical, strain tensor has to be symmetrical, because they are related by elastic constants. Similarly, strain tensor is symmetrical, that's why stress tensor is symmetrical. So you have arrived at the right approach, that from this approach you are getting the strain tensor as a symmetrical tensor and how it should be, because stress tensor is also symmetrical. And you see, in the strain tensor, you are finding there are 6 independent strain components. You need to know the normal strain and 3 shear strain. So total 6 independent strain components, like the stress tensor. Look into the rotational tensor Rij. What is the first term of the second row? The first term of the second row is, you see, what will be that term? That term is Eyx minus Exy by 2. So it comes out as del V del X minus del U del Y by 2. Whereas this term is del U del Y minus del V del X by 2. So these two are not equal. So these two are not equal. And this is represented by the minus sign as expected in rotation. So this is the asymmetrical part of that relative displacement tensor, which is the rotational tensor, whereas the symmetrical part is your strain tensor. So this is a very important thing that we have derived, and the strain tensor can be represented in this form: epsilon xx, epsilon xy, epsilon xz. Xy are the same, that's why I am writing this as the same way. Then yy, yz, yz same, xz same. So it's a symmetrical tensor. Strain tensor is a symmetrical tensor. And often in place of this xy shear strain, the term gamma is used. So instead of epsilon xy, often it is represented by gamma xy, where gamma xy basically represents the total angular change on the plane. So gamma xy equal to 2 into epsilon xy, equal to 2 into epsilon yx, because xy and yx are the same. Similarly, gamma xz equal to 2 into epsilon xz. Gamma yz equal to 2 into epsilon yz. So on the yz plane, what is the total angular change if you apply all kind of stress? That is represented by gamma yz or gamma xz, which is epsilon xy plus epsilon yx. So 2 into epsilon xy. So gamma term means you just need to remove the term 2 from the displacement term. So gamma xy, that means del u del y plus del v del x, del u del y plus del v del x. Similarly, gamma xz is del u del z plus del w del x. Gamma yz is del v del z plus del w del y. So this is how shear strains are represented. Shear strains are represented by the term gamma, and normal strain are represented by, as usual, epsilon xx. What is epsilon xx? Del u del x. Epsilon yy del v del y. Epsilon zz del w del z. Very nice. Now it's time to relate stress tensor with strain tensor. Relate, because ultimately we have to establish the relation between these two tensor, because basically they are completely related. If I give you stress tensor, you can derive strain tensor. If I give you stress tensor, from that you can derive the principal stress values, and from that you can even tell me that, teacher, what is the value of uniaxial tensile yield strength. If I provide, you will be able to tell for that stress tensor yielding will occur or not. Similarly, if I give you stress tensor, you can calculate strain tensor. If I give you strain tensor, you can back calculate the stress tensor, and from that you can derive whether yielding will occur or not. So if you see in a body some amount of displacement, because we said that ultimately things that we measure is displacement. Inside a bridge, we put certain gauge. Different types of gauge are put inside a bridge, and the civil engineers monitor the displacement in the form of a movement of liquid inside that those gauges, and from that they know what are the strain components, how much is the displacement taking place or strain taking place, and from that they actually derive the stress tensor. Because we said that we cannot directly know what is the stress until and unless we see the strain. What we measure is the strain. So you do measurement of strain and you can calculate the stress tensor, and from that you can check the yield criteria and other things. So all are related, and to understand that relation, you first again look into this plot xy axis, where red dotted line is my initial body, which is I am applying a stress. And what is the stress that I am applying? You know that stress is sigma xx, because it is acting on the x plane, the plane that is perpendicular to the x direction, and it is acting along the direction x. So that stress component is my sigma xx. And because of sigma xx, what are the strain components that I am getting? I am getting a strain component epsilon xx, and I am also getting a strain component minus epsilon of yy. Let us have a look in the second plot. What we are trying to show is I am applying a shear stress, what I am writing as tau xy. Because it is acting on x plane in the y direction, and tau xy, we know that it is basically same as tau yx. Tau xy and tau yx is the same. So as a result, what strain I am getting, the strain component is epsilon yx, which is again equal to epsilon xy, and gamma xy or gamma yx equal to 2 times of epsilon yx or 2 times of epsilon xy. So one thing we are finding is normal stress sigma xx is causing normal strain. If sigma xx is causing components like epsilon xx or epsilon yy. On the other hand, shear stress, when I'm applying shear stress, it is not causing any normal strain. Shear stress is causing shear strain. Tau xy, tau yx will be causing corresponding epsilon or gamma components. Gamma is nothing but 2 times of the epsilon xy component. So in general, the stress strain relationship under elastic loading condition can be represented by these equations. The name of these sets of equations are written here. Very important expressions. This is called constitutive equations. Constitutive equations under elastic condition. Remember, this is applicable to elastic condition, and in plastic condition also these values will not be much different. The relation will not be much different. I will tell you what is the small difference that will be there under plastic condition. So constitutive equations are these equations. You can see the first expression, epsilon 11 equal to sigma 11 by E minus nu by E sigma 22 plus sigma 33. What is nu? Nu is the Poisson's ratio. Poisson's ratio. Poisson's ratio is the ratio between transverse strain to the longitudinal strain. If I apply sigma xx, then there will be longitudinal strain of epsilon xx and transverse strain of epsilon yy along y direction. And if there is a z direction strain also, that is epsilon zz. So epsilon yy by epsilon xx or epsilon zz by epsilon xx, that is the Poisson's ratio, the ratio between transverse strain to longitudinal strain. So this tells that where from epsilon 11 strain component can come or epsilon xx strain component can come. This tells that it can certainly come when there is a normal stress along that direction, sigma xx component. Sigma xx causes epsilon xx, but some other components can also cause that same strain component, epsilon xx, and those are sigma 22 and sigma 33, and then they will be related by Poisson's ratio, because sigma 22 will directly cause epsilon 22, but the body will also shrink in the direction 1, so there will be an epsilon 11 as a transverse strain. So that relation will be estimated by this nu by E term, where E is the Young's modulus. Similarly, epsilon 22 equal to sigma 22 by E minus nu by E sigma 11 plus sigma 33. Epsilon 33 equal to sigma 33 by E minus nu by E sigma 11 plus sigma 22. And this is how the normal stress and normal strain are related. And this is how the shear stress and shear strain are related. So all the terms of the strain tensor are related to all the terms of the stress tensor. Gamma 12 equal to tau 12 by G. Basically, gamma 12 equal to 2 into epsilon 12. Similarly, gamma 23 equal to tau 23 by G equal to 2 into epsilon 23. Gamma 13 equal to gamma tau 13 by G equal to 2 into epsilon 13. So shear stress leads to the corresponding shear strain component, whereas normal stress leads to normal strain components. Along with that corresponding components is also leads to other components, two other components as well. So this is how stress tensor and strain tensor can be related through elastic constants. Now, what we are showing in this cube, this is my suppose a small volume element I am taking with volume dx dy dz. The body as a small cube I am taking, parallelepiped I am taking with x direction length is dx, y direction length is dy, and z direction length is dz. The total volume is dx dy dz. Now, if it goes to a small amount of deformation, suppose it goes to small amount of deformation. What will be my volume change? That I want to calculate. So to calculate the volume change, how much will be the change in dimension in every major axis direction? So initially along x direction its length was dx. Now that length will increase or decrease to dx plus dx into 1 plus epsilon xx. If there is a small amount of strain along x direction and proportional to x is epsilon xx, so there dx is increasing by a small amount, say 1 plus epsilon xx. Similarly, dy is increasing by a small amount of dy plus into 1 plus epsilon yy. dz is increasing by a small amount to dz into 1 plus epsilon zz. So the change in dimension that is happening is epsilon xx into dx, epsilon yy into dy, epsilon zz into dz. So now what is the new volume? If you multiply these three terms, then you will get the new volume is dx dy dz into 1 plus epsilon xx plus epsilon yy plus epsilon zz, where I am ignoring the multiplying terms because I have assumed these strain values are quite small in fraction. So epsilon xx epsilon yy or epsilon xx epsilon yy epsilon zz, these double or triple multiplying factors I am ignoring. I'm just taking the first value. So the new volume you will get dx dy dz into 1 plus epsilon xx plus epsilon yy plus epsilon zz. How much is the volume change? You have to subtract by initial volume. You have to divide it by initial volume to get delta, and delta is representing the volume strain. Delta is representing volume strain. So volume strain can be the simple addition of the normal strain values. This I want to show, that if there is a volume change, volume strain is the simple addition of the normal strain values. Epsilon xx, epsilon yy plus epsilon zz is the volume strain. Now if these three expression you take normal stress normal strain relations, if you simply add them, what will come? You will get epsilon 1 plus epsilon 2 plus epsilon 3 which is basically volume strain delta, equals to 1 minus 2 nu by E sigma 1 plus sigma 2 plus sigma 3. And if you know that this term, if you divide it by 3, that gives you hydrostatic stress. Average of normal stress is hydrostatic stress. So sigma 1 plus sigma 2 plus sigma 3 by 3 is your hydrostatic stress. Since you have divided 3 here, you have to multiply 3 here. So the ratio of hydrostatic stress sigma h and volume strain delta is known as what? Is known as bulk modulus. It is known as bulk modulus, and bulk modulus is equal to E by 3 into 1 minus 2 nu. So you see, different modulus are actually related to each other. Similarly, E and G are related. Elastic modulus and shear modulus are related. So it is an interesting observation that out of these, here we are talking about 4 modulus values, E, G, nu and K. Out of these 4 modulus values, if you know any 2 values, you will be able to derive all the other values because they are related by simple expression. Remember this is an interesting observation. Now, when there is plastic deformation, in elastic deformation, small amount of volume change can be permitted. But in case of plastic deformation, we know that volume remains constant. So the delta terms will become 0. The total volume strain terms will become 0. So if these terms become 0, then sigma 11 plus sigma 22 plus sigma 33 term, it's not necessary for this sum of the normal stresses to be 0. If the total volume strain has to be 0, then it is not necessary that sigma 11, sigma 22, sigma 33 is basically your stress tensor component, and their sum need not be 0. That may be 0, but there is a high chance that will not be 0. That can be positive or that can be negative. Then if the volume remains constant under plastic deformation, what factor has to be 0? Then must be this factor has to be 0. So 1 minus 2 nu by E must be 0. This condition needs to be satisfied for volume strain to be 0 at all the time. So from that we get the value nu equal to half. Nu equal to half. So when a body is plastically deforming, nu is Poisson's ratio is equal to half. So the amount of transverse strain that you get in negative direction is half of the normal strain along the longitudinal strain. So when plastic deformation happens to a tensile specimen, the epsilon YY or epsilon ZZ that you get is basically half of the amount of longitudinal strain that you are that the specimen is elongating. So remember, under plastic deformation condition, nu equal to half, and similar expressions hold. Similar expression hold only since plastic deformation is incremental. Therefore, instead of epsilon we write d epsilon. D epsilon, the coefficients change a little, effective stress and effective strain value comes, but basic expression remains the same. So if this term is 0, you can write that sigma 33 equal to sigma 11 plus sigma 22 by 2, because under plastic deformation condition, nu equal to half. For elastic deformation condition, nu value depends on the material. So very similar expression hold in plastic deformation condition, where epsilon 33 you have to write d epsilon 33 because plastic increment is small and nu value is half, with coefficients values little different. But same way these hold, and that expression is called Levi-Mises expressions. In my PPT presentation, you will find Levi-Mises expressions written. Just to have that concept in mind. So let us come back to the PowerPoint presentation where everything is written and will be shared with you. You see, specimen tensor EIJ comprises of translation, rotation, and strain. Translation can be taken into account by changing the coordinate system axis. Now you divide it into a symmetrical part with a positive sign and asymmetrical part with a negative sign. Asymmetrical part will take care of your rotational tensor and positive sign will take care of your strain tensor. Stress tensor is symmetrical tensor, hence strain tensor is also a symmetrical tensor. Coming to next slide, we have shown different kinds of conditions. What I have discussed with you so far. We are showing here that stress tensor is a symmetrical tensor. Strain tensor is a symmetrical tensor. E12 plus E21 by 2. Here also E12 plus E21 by 2. Third term of the first row and first term of the third row, third term of the second row and second term of the third row, they are equal. So there are 6 net values. And here we are showing deformation. The body is deforming. Clearly the square body has deformed. On the other hand, it is rotated. So the total angular change is the minus of these two displacement components, whereas here is the plus of these two displacement component. Strain tensor. Total angular change is represented by gamma. Coming to the constitutive equation, the same expressions are written in this form. The same expressions are written. All the expressions are written. Sigma 12 equal to G into gamma 12, or tau 12, better to write. Tau 13 equal to G into gamma 13. Tau 23 equal to G into gamma 23. How E and G are related? G equal to E by 2 into 1 plus nu. So shear modulus equal to elastic modulus divided by 2 into 1 plus Poisson's ratio. This is the way it is related. Sometimes these constitutive equations, all the equations can be represented in a generalized form. If you can see the generalized form, it's very easy to remember. Epsilon ij, where ij are any term between 1, 2, and 3, equal to 1 plus nu by E sigma ij minus nu by E sigma kk. Sigma kk equal to sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 plus delta ij. Delta ij is called Konecker delta, which is a form, which is a tensor form 1, 0, 0, 0, 1, 0, 0, 0, 1. That means when we are considering normal stress and strain, the second part of the expression will be there. Minus nu by E sigma kk delta ij will be there when normal stress and strain are related. You see, when normal stress and strain are related, the second term is there. Whereas when shear stress and strain are related, that part is not there. So for those, this value is 0. And if I take epsilon 1, 2 equal to 1 plus gamma by E, 1 plus nu by E sigma 1, 2. And 1 plus nu by E means 1 by 2g. So here if you write 1 by 2g, it will come out as tau 12 equal to g into gamma 12. Similarly, if you write epsilon 11 equal to 1 plus nu by E sigma 11 minus nu by E sigma 11 plus sigma 22 plus sigma 33 into 1. That will give you this expression, sigma 11 by E minus nu by E sigma 22 plus sigma 33. So this is the generalized form. Sometimes it is written in this way, generalized way, same thing. Similarly, stress can be represented by strain. In the earlier constitutive equation, we are representing strain in terms of stress components. Strain components in the left hand side, stress components in the right hand side. Similar thing we can do. We can take the stress component in the left hand side and strain components in the right hand side. If I give you strain tensor, you can calculate the stress tensor values. The same generalized form can be used where lambda is called Lami's constant. Here is lambda, Lami's constant, nu E by 1 plus E, 1 plus nu into 1 minus 2 nu. Delta is the volume strain, epsilon 11 plus epsilon 22 plus epsilon 33. And Konecker delta is again just telling that for normal stress and strain, this second term will be there. For shear, the second term will not be there. So for isotropic solid, 2 points are valid. Only 2 elastic constants are sufficient. So far, what we are discussing is isotropic solid. At the beginning of the course, we have used certain word, continuous, homogeneous, and isotropic. So all these expressions are applicable to isotropic conditions. We have one assumption that we are using an isotropic body, but the property is same and elastic constants is same along all the directions. But whenever we see real crystal starting from cubic to triclinic, if you go along, the degree of anisotropy increases. So in a cubic, even if you consider a cubic crystal, if you take 100 direction, the atom spacing, if you take 111 direction, the atom spacing is different. And that's why the Young's modulus values or elastic constants can be different along different direction. So you need to know more number of elastic constant to represent stress and strain, to relate stress and strain tensor. So among the real crystal structures that we get, cubic is the most symmetrical. So there you need 3 elastic constants. In real cubic material, you need to know 3. That's why E, G, and nu is reported. For isotropic, if you know only 2, that will be good enough. But the most anisotropic is triclinic, where you need to know as many as 21 elastic constants. In hexagonal, you need to know 6 elastic constants, and so on. Here we are proving that volume strain equal to sigma 1 plus sigma 2 plus sigma 2 3 normal strain, as we have derived already. Here we are deriving the bulk modulus as a ratio of hydrostatic stress by volume strain, that we have done already. This is an interesting and important understanding. Let me quickly go back to the Canvas screen again, because I have prepared one slide on this thing. Depending on the size of the specimen, I have told you, depending on the size of specimen, the loading condition changes. If I use a thin and specimen, not very wide, then I have said that if you apply an uniaxial stress, it will be really uniaxial. On the other hand, if you use a thick specimen, then there will be more constraint, or if there is a notch, then there will be more constraint and your loading will become triaxial. As you have understanding of von Mises criteria now, you can understand that it is simply uniaxial for the yielding to occur. Principal stress sigma 1 has to exceed sigma naught. But if the body is thick, then the constraint imposed by the other directions will introduce positive values of sigma 2 and sigma 3, resist the shrinking of the body along these 2 directions. Because you know, if you apply sigma 1 1, there will be an epsilon 1 1 along positive direction, but there will be epsilon 2 2 and epsilon 3 3 in negative direction. The body has to squeeze in those 2 axes. But if you apply, if you apply, or if it happens that there are positive stresses acting along those direction 2 and direction 3, then the specimen will not be squeezed in that way and it will be resisted. So simply in the von Mises criteria, if you introduce high value of sigma 2 and high value of sigma 3 positive value, you will find sigma 1 value has to be much higher than the yield strength to cause plastic deformation for the von Mises criteria to be satisfied. And that aspect is called plastic constraint factor, PCF. In plane strain, the yield strength is about 3 times. It can go up to 3 times if there is a notch under plane strain condition. In general, if a body is deforming under plane strain, the yield strength is 1.15 times higher than the stress required for under uniaxial tensile loading. So what is plane stress? As I said, if the body is under plane stress, that means either uniaxial or biaxial loading of a sheet of a thin specimen. So along the plane stress, along the third direction, there is no stress. Along the third direction, there is no stress. That is called plane stress. But if along the third direction there is no stress, will there be any strain along the third direction? Yes, there can be. We know these two values will not be there because sigma epsilon 13 requires sigma 13, epsilon 23 requires sigma 23, but epsilon 33, even sigma 11 or sigma 22 can give you epsilon 33. Epsilon 33 equal to sigma 33 by E minus nu by E sigma 11 plus sigma 22 from the constitutive equation. So if you apply sigma 11, there can be epsilon 33. So if a body under plane stress, it may be under plane strain if epsilon 33 is 0 by chance, depends on how the value of epsilon 11 and 22, but it may not be under plane strain also. Epsilon 33 term can be there. When you work with a larger volume of material, if you apply stress, I have said, if a particular volume of material has to deform, it has to shrink, and the surrounding region will apply a constraint on it. So you will find along the 3 direction, if it is wide and thick, 3 direction, such restriction is coming. And if it is very wide, what will happen? It will not shrink in the width direction. So there will not be any strain in the width direction. Similarly, when we do rolling, when you deform a particular volume of material under roll, its height decreases, its length increases, but it also likes to extend in its width because the excess metal has to reduce its height and the excess metal has to elongate the length and elongate the width. But the width elongation will be resisted by this part of undeformed metal, which will apply a constraint. So you will find there is no change in width. And that is called plane strain. Similarly, a very wide specimen containing a notch, if you deform, then the notch root material would like to expand because the maximum stress working at the notch root, it has to expand. So to expand, it has to contract from this side also, and it likes to contract from this side also. If your width is very large, then it cannot contract in the width side because the material away from that notch root will apply a constraint. If your thickness is very large, it will even not change in thickness because there will be constraint. So that kind of condition is called plane strain condition. And under plane strain condition, that means strain is there only in 2 dimensions. On a plane it is acting. The third dimension strain is 0. But you will find the third dimension there can be stress. So if it is plane stress, it need not be in plane strain. If it is plane strain, it need not be in plane strains. But have understanding of these two aspects, because plane strain basically introduces stress along the 2 other direction by resisting the strain along those 2 directions, and increases the yield strength of the material following von Mises criteria or even Tresca's criteria if you consider. Now I think you have a good understanding on the entire thing. I request you to go through the Mohr circle concept. Not everything is possible for me to cover under this limited time. You have good understanding of normal stress, shear stress, applied stress, stress tensor component, principal stress components. Like constitutive equation relates normal stress and normal strain, it also in the same way relate principal stress. Principal stress are basically normal stresses on the planes where shear stress equal to 0. So as there is principal stress with respect to those planes, if you take that cube, principal plane cube, there will be a principal strain also. There will be strain along these three directions also. So in the same way, as normal stress and normal strain are related, principal stress and principal strain can be related in the same way. Epsilon Roman 1 equal to sigma Roman 1 by E minus nu by E sigma Roman 2 plus sigma Roman 3, like three normal equations. And there is no shear in principle, because principle means there is no shear. Please go through Mohr circle. I may ask you brief concepts. There is one important consideration called distortion energy. What is distortion energy? Let me again quickly go back to the Canvas screen, the slide that I have made to make you understand distortion energy. Distortion energy means elastic strain energy absorbed by a body. So what is elastic strain energy? We know there is a stress strain curve, and the area under the curve, under the elastic region, represents the, if you draw a straight line from here, that area represents the elastic strain energy accommodated by the specimen, which is also called resilience. So if you have sigma, if you have epsilon, how the elastic strain energy is represented? Elastic strain energy is represented as half into sigma into epsilon, the area under the curve. And the unit is, please remember, joule per meter cube. This is elastic strain energy per unit volume, because stress has an unit of force by area, Newton per meter square. Strain, sorry, epsilon. This is epsilon. Strain has an unit of meter by meter. Strain doesn't have any unit, so meter by meter. So it comes to Newton meter. Newton meter, sigma into epsilon, half sigma epsilon. So you get Newton meter by meter cube, which is joule per meter cube, the area under the curve. So you can calculate from the stress strain curve sigma into half sigma into epsilon is my distortion energy or elastic strain energy. But now actually you know sigma is not a single sigma. The sigma that we express in tension test is basically your principal applied stress, sigma Roman 1. And strain that we measure is basically the epsilon Roman 1, the principal strain. With respect to the cross-sectional plane is basically your principal plane on which maximum principal stress applies, sigma Roman 1. On the other two principal plane, there is no stress, Roman 2, Roman 3 equal to 0. But you know that in a complex loading condition, it's not necessarily every loading will be simple tension. You may have a very complex loading, this side loading like a bridge or like a structure, like your building goes through different types of loading in different direction. You are sitting in a chair, someone is pushing you, trying to fall down, your weight is heavy, someone is pushing from behind. So in class that happens. So it's a complex loading. So whenever there is a complex loading, you have to consider the generalized case. That means you have to consider the stress tensor multiplied by the strain tensor. All the components you need to think. Stress tensor multiplied by strain tensor. Now, this distortion energy you can write completely in the form of stress tensor terms, completely in the form of strain tensor term. Suppose I write it in the form of completely stress tensor term, Ij. What I have to do? I know the relation between stress and strain. So strain tensor terms I will write in the form of stress tensor terms. 1 plus nu by E sigma ij minus nu by E sigma kk delta ij. Delta is a Koenig delta, sigma kk is sum of the normal strain, as I have told. The entire expression will be full of stress tensor terms. And if you have the stress tensor values, you can calculate in number per unit volume. Similarly, I can give you the, in place of stress, you can write strain tensor terms. Sigma ij equal to 2g epsilon ij plus nu plus lambda delta Koenig delta. You can write that. But one beauty will be there. Del u naught, if you do derivative with respect to any strain term, you will get the corresponding strain stress term, and vice versa. If you do the derivative, the expression that you will get, if you do the derivative with respect to any strain component, you will get the corresponding stress component. Similarly, if you do derivative with respect to a stress component, you will get a corresponding strain component. For example, del u naught by del epsilon xx, you will get sigma xx. Similarly, del u naught by del sigma xx, you will get epsilon xx. If you do derivative with respect to epsilon xy, you will get sigma xy. That is the beauty. And I am showing in my PowerPoint slide, the entire term is written in the form of here. If you can see my PowerPoint pointer, U is represented completely in the form of stress component terms. On the other hand, below, U is written completely in the form of strain component terms, epsilon and gamma. And as I said, if you do the derivative with respect to epsilon xx, you will get the corresponding stress term, and vice versa. So distortion energy, you need to have an understanding for generalized condition, because uniaxial tension is the most simple condition, whereas any complex loading can be represented by the stress tensor and strain tensor. Von Mises said one more thing. He said yielding will occur when distortion energy reaches a critical value. So the distortion energy, that values we have obtained, that expressions, if we represent them in the form of principal stress terms, you will find it is coming out to be u naught equal to 1 by 12g sigma 1 Roman 1 minus Roman 2 square plus Roman 2 minus Roman 3 square plus Roman 3 minus Roman 1 square. So that was another interpretation of von Mises, that von Mises also said that yielding occurs when the distortion energy exceeds the critical value. Like he said that yielding will occur when second invariant of stress deviator exceeds the critical value. Here he said when distortion energy exceeds the critical value. And how to get that critical value? Equal to K. That critical value you take as C or K, whatever, and you use the most simple condition, which is uniaxial tension, where sigma Roman 1 has to exceed sigma naught for the yielding to occur, where sigma 2 and sigma 3 will be 0. So you will get the value of K. And if you get the value of K, you will get back the von Mises expression. The same expression will come back 1 by root 2 sigma 1 minus sigma 2 square plus 2 minus 3 square plus 3 minus 1 square greater than equal to sigma naught. Same form as derived earlier. So in both way you come, you will arrive at the same final expression. Some useful stress strain expressions that we represent something we called effective stress. The von Mises expression, the left hand term is called von Mises effective stress. When von Mises effective stress exceeds the uniaxial yield strength, yielding will occur. So this is effective stress. Similarly, there is in plastic deformation condition, I have said epsilon principal strains are represented in terms of d epsilon, small increment. So there is an effective strain also that can be simplified and represented in different forms. I'm not going in detail of Levi-Mises expression, but the final expressions you see, it is very same type like constitutive equation. D epsilon 1 equal to effective stress by average stress, or effective stress, effective strain by effective stress, sigma 1 minus half, because Poisson's ratio equal to half when plastic deformation, sigma 2 plus sigma 3. So if it is plane strain, you consider d epsilon 3 equal to 0, you will get sigma 3 equal to sigma 1 plus sigma 2 by 2. In place of sigma 3, you put that in von Mises criteria, you will get sigma 1 minus sigma 2 equal to 1.15 sigma naught, which is the form of Tresca's criteria. So under plane strain, it is said that von Mises and Tresca criteria following the same form, and yield strength under plane strain condition is 15% higher than the yield strength in uniaxial tension. Just two more slides. So far we have talked about isotropic material, where there are two elastic constants. If you know, all job done. But actually, how many elastic constants should be there? You know actually how many stress, because elastic constants relate to stress tensor with strain tensor in a generalized way. So ideally, if you consider completely random stress tensor and relate with the strain tensor using elastic constants, there have to be 9 stress components and 9 strain components. So ideally, there will be 9 into 9. This is 9 order tensor. The elastic stiffness tensor will be 9 order tensor. 9 into 9, 81 components. So stress and strain are related by stiffness. So Cij is called stiffness tensor. Similarly, if you represent epsilon equals to constant into stress tensor, that is called compliance tensor, and compliance tensor is Sij. Mark this difference. C doesn't mean compliance. S means compliance tensor. C is stiffness tensor, elastic stiffness tensor. So sigma I equal to stress tensor equal to stiffness tensor into epsilon strain tensor. Strain tensor equal to compliance into stress tensor. So ideally there should be 81 components, but you know that how many independent components? There are 6 independent strain, and that's why you need not have to know 81 components, elastic constants. So it's a 6 values of stress has to be related to 6 values of strain. So you can write sigma 1 equal to C1 1 epsilon 1 1 plus C1 2 epsilon 2 2 C1 3 epsilon 3 3 C1 4 epsilon 1 4 like that. Epsilon 1 2 1 3 2 3. So 36 terms will be good enough. If you know 36, 6 by 6. So the size of the stiffness tensor comes down to 6 by 6. Now, As I said, there is one more relation. If you do a derivative of distortion energy with respect to a particular strain component, you get back the particular stress component. And that stress component you expand. So del U by del epsilon 1 you will get sigma 1 and you can write it as C11 epsilon 1 2 epsilon 2 2 1 3 epsilon 3 3 1 4 gamma 2 3 gamma 1 3 like that. If you do double derivative, you will get back C12, a particular stiffness constant that you will get, that is C12. Similarly, if you do one more thing, that del U by del epsilon 2 if you do derivative with respect to epsilon 2 now in place of sigma epsilon 1 then you get sigma 2 you expand, you write sigma 2 in the form of strain components and elastic constants, stiffness constants, and take a double derivative of that with respect to 1 epsilon 1. Here you take a double derivative with respect to epsilon 2 you will get C12. If you take first derivative with respect to epsilon 2, next derivative with respect to epsilon 1, you will get C21. So since double derivative of U with respect to 1 and 2 strain equal to double derivative of U with respect to 2 and 1 strain, these two are also equal. These two terms are also equal. So that means the 36 term that you get, the tensor, the stiffness tensor that you get, 1 2 equal to 2 1, 1 3 equal to 3 1. That means it is also a symmetrical tensor. The elastic will also be a symmetrical tensor. So if it is a symmetrical tensor, how many independent values you need to know? If it is symmetrical with respect to diagonal 1 1 2 2 3 3 4 4 5 5 6 6, you need to know must. And then how many values you need to know that represent the entire tensor? You need to know the values of any one side of the diagonal, all the values along the diagonal and any one side of the diagonal. So total 6, remain 30. So remaining 30, if you know 30 by 2, 15 values, you can determine write down the entire stiffness tensor. So basically 15 plus 6 equal to 21 stiffness constants is the maximum requirement. And when so many stiffness constants you need to know to relate stress tensor and strain tensor? When your structure is most anisotropic. And when it is most anisotropic among the crystal systems? When it is triclinic. When it is triclinic. And when it is more close to isotropic, because isotropy is a virtual, it's an ideal condition. Real material do not be perfectly isotropic. What is the most close to isotropic condition is cubic. So you see the number of elastic constant, independent elastic constant that you need to know: triclinic 21, monoclinic 13, orthorhombic 9, tetragonal 6, hexagonal 5, cubic 3, and isotropic, which is ideal 2. So I request you to please go through these 2 lectures. These were quite extensive, more than 1.5 hours. But these are very important aspects to understand. I give you time till Thursday night to go through these 2 lectures, because the derivation that we will start on Friday requires this understanding: stress tensor, strain tensor, and their relationship. You even need to know the displacement that we represented, U, V, W. So by Thursday night, you please be clear about these 2 lectures. Read you watch the videos, you take necessary notes. Videos will be uploaded now only. I will share with you the slides. So everything is written there. Just if you listen to this and read the slide, everything will be very clear. So the recording may be stopped, Shubham.